Please follow me.
Hi, how you doing? Good. So this is our final system reveal. We're currently on the title page, so I'll let you know when we're switching over, but we are the Me415 acronym class, and we will be going over our final rock crusher system. You'll go ahead and switch the slide.
Great.
This is our final design. Our total cost is about $960. We have our 4 subsystems in total, as we've spoken to you about. And the general procedure for operating the machine is the rocks are fed through the hopper, feeding down to the crusher. Through the flywheel, we're able to turn that, crushing the rocks, and from there they move to the sifting mechanism, which it moves out to wherever they want to organize the rocks. Go ahead and flip the slide, and we'll pass it off to the power system.
So for the power system, we wanted something simple and easy. We decided to go with a wooden flywheel made of plywood. It allows it to be replaced fairly easy, and the hardware is really cheap. For this one wheel, the total cost was $69.96, and that included labor and stuff at the place we got it cut. There's a rotating metal handle that sits on the outside of the wheel. You turn it, and the energy from that rotates through the shaft, and then goes through and crushes the rock. It's a 2.5-foot diameter wheel, so it allows you to kind of get your entire body into it and get a lot of force transfer through that.
Go ahead, and next slide.
So yeah, the crushing system costed just under $700. The main purpose with the crushing system was to be able to maintain it. So in order to do that, we added teeth that were indexable. So over time, as the teeth crushed, we'd be able to index them and go to a new side where it was a fresh surface. So basically how it works, coming from the power system, it goes into the rock crusher, and then we feed the rocks in, and then the barrel starts to crush it based on the torque from the power system, and then by then it goes into the sifting unit and is divided out from there. So with that being said, I'm going to pass it on to the sifting team.
So the total cost of our system was just under $80, and it sits right underneath the crusher where the rocks fall out, and they fall onto just this wire mesh that's around a 2x4 frame, and the small rocks fall through and then onto a slide that diverts them into one pile or into a bucket if they wanted to. And so those are the rocks they're going to sell, and then the larger ones will just slide off into another area, and they just move those back through. Ours is pretty easy to maintain. Really, the only thing that's going to wear out is the wire mesh, and that's pretty cheap and quick to fix. And even if one wire breaks, you can run a single wire through if you wanted.
Alrighty. And we'll pass off to the next slide. So for the frame system, our total cost is about $115. It's a totally welded system, so to mitigate fractures and with many support members. It's basically just a static structure it's meant to contain all the subsystems. The maintenance issues could be pretty great with the subsystem, as everything is welded. So to replace anything, you're going to have to cut a piece out and then re-weld it, creating a lot of issues. Therefore, the system was had a lot of engineering analysis conducted on it to make sure that it had the static strength to help it against any sort of fatigue failure. We'll go ahead, next slide.
So for the bill of materials, as Matt said in the beginning, it was about $900 for this whole entire system. Many of the parts that we had gathered were from either the Pullman Building Supply and other local establishments, or McMasterCard, which is online. Those, with the shipping days, it was average about 2 or 3 days for us, so it was pretty easy for us to gather all of the materials that we need, and so we could build and create the system pretty quickly.
All right, next slide.
So for the cost analysis, quite a few assumptions are made and are confirmed by the professor that are adequate assumptions to make. For this cost analysis, 2 things that I want to highlight is one, ELF truck, we can get about 80,000 shillings, which was expressed to us by the client at the beginning of the semester. If you convert that to US dollars, it's about $22.40 for one truckload. Another assumption that we made is that in a week, we will have 6 days that will be working days. So that accumulates over a year's time to be 313 days. The rest of these assumptions are based off of what material we are using, the benefit-cost ratio. We will be setting that equal to 1 to figure out how much the clients are going to be making themselves, how the dimensions are for the ELF truck, because we need to fill up one ELF truck dimension for the bed. So this is the dimensions of that, what the capacity is of that, what the density is of the marble, or the most costly or high-priced product that will be sold. So we're basing this off of what they could get the most money out of for the material. So if we go to the next slide, we can calculate trying to go to the next slide. Give us a second. Okay, so in this presentation, we have multiple scenarios set up because we have had some difficulties manufacturing since we're coming towards the end of the semester. A lot of our time is limited, and manufacturing this has taken quite a bit of time. So I think we got almost a full assembly done by yesterday, but we don't have an output rate. So we can crush rocks. We don't know how fast we can crush rocks. So once we have that time, we can then calculate how much money we can get in a year's time. So these are 4 scenarios that are approved by our professor that are ideal scenarios that we can look over. One scenario being the best option. We have a lifespan of the rock crusher being 5 years' time, and we're assuming that it can fill up a truck in half a day's time. So you can fill up 2 trucks in a day. Another scenario is the lifespan is 2 years, and it can fill a truck in 2 days. And then in scenario C, we have the worst projection. It only has a lifespan of 1 year, and it takes 3 days to fill it. The reason why I say this one's the worst is because if I put that to 4 days, we actually saw the employees losing money. So scenario D is our ideal projection. This is the projection that we started out with in the beginning. We all set, the entire class set our projection to hopefully fill up a truck's bed load in 1 day's time. And then 3 years of a lifespan is just a very good general average setting for that. Right now what we're seeing is that the operator salaries, so the clients make about $2 a week, and that roughly comes to $104. Let's go to the next slide. So the way we calculated benefit is how much we can sell our product for, so a full truck bed, by multiplying it by the number of working days, and then we divide that by how long it takes us to fill up a bed load. So that's dependent on our output, which we don't know yet. So we know how much our product sells. That's $22.40. We know that's 313 days for us to work in a year. Go to the next slide. And with our initial cost, we're basing this off of what Jackie said for the bill of materials is $960.31. We are also going to be multiplying that by our annual compared to present interest rate with the lifespan. So we're going to be changing the lifespan now. The interest rate, I made 10%. I looked up in Uganda that right now, as of November, the interest rate in Uganda is 9.5%, but we don't have that available in our tables. We have 10%, so I rounded up. We also made a assumption that the number of operators for this in a day's time will be 8. 1 person to crank it, 1 person to sift it, another 2 people to comfortably lift it and transport it, and then 2 shifts in a day. So 8 people total. And our maintenance cost was also, which would be replacement parts, such as the teeth that will be on the barrel, which will be coming in contact with the marble and being affected the most because it's going to be hitting the rock and having the most wear on it. So the replaceable parts really came out to be at $250 in a year's time. So if we apply all scenarios into this, and if you go to the next slide, have our benefit cost ratio equal to 1. You can either equal it to 1 or have it greater. That's the most ideal. But this way we can calculate how much our operators are getting an annual salary. So if we set it equal to 1 and over these different scenarios, for the best scenario, we find each operator gets about almost $1,700. In our suitable scenario, where they're having a lifespan of 2 years and they can fill a bed, a truck bed in 2 days, we can see that they're coming to $337. In our worst scenario, which is just over how much they're making right now, $140. As I said earlier, our clients are making $104 as right now. So if we have our ideal, which we wanted in the beginning, was 1 day to fill up a truck bed with a lifespan of 3 years, that could look better if the mechanism lasts for 5 years. We don't know that, but we come up to about $800. And so these scenarios give us the projection of what we could have, our best, our not so great, and then our worst, and then our ideal situations. And once we actually calculate how long it takes for us to get an output of our rock crushers, the way we're going to do that is we purchased white marble chips, and once we run that through, the size is about 3 cubic feet. We can run that through, check the density of the marble, multiply it through, and compare that ratio to how long it would take us to fill a bed, a truck bed. And once we get that time, then we can calculate how long it would take, or how much we can accumulate. And that's the presentation. Do you have any questions?
Great. Well, thank you very much. Can you hear me okay?
Yes.
Yes.
Okay, great. Yeah, just a few. Well, first I want to thank you and everyone in the class and the teachers for doing this. I think it's a really cool project. Not only from an academic point of view and a construction point of view, but much more importantly from a practical point of view. I mean, this is what you're designing is really cool, and I think to have it in mind of the ultimate goal, I think is really important. So thanks, and thanks for all the work you put into it. So just maybe a few questions, and your professor sent me a picture of it, the rock crusher poster, and it looks really cool. Is that the final what I'm staring at right now? It's kind of the mid panel. Is that the final product?
The poster is.
Yes.
Yeah.
It's a poster. I'm looking at a poster right now. Yeah.
Okay.
So yeah, it looks really cool. So with the different scenarios, 5 years, 2 years, 1 year, and 3 years. Did you how did you come up with them, or maybe do you have a sense, just maybe say rough rule of thumb, what you would expect the lifetime to be? Is it more on the 5 years, more on the 1 year?
That was one thing that we were questioning, and I actually asked the professor what would be a good assumption to base this off of, because we don't know how much the rocks are actually going to fatigue this mechanism until we actually do some testing. But
right.
Our professor helped me out and said it's okay to do just say let's do 1, 3, and 5, and then I added into it.
Yeah. Yeah. No, I completely agree. It's a really good way of approaching it, because you don't know. There's some uncertainty, so you have different scenarios. So yeah, no, completely agree. So it's good to see this comparison. So I was just curious of where it might lean. So if I'm getting I'm taking a look at the cost analysis now. So if I'm understanding it correctly, given these 4 scenarios, you're calculating really how much each of the operators would make in a given year?
Yes.
Okay. And the third scenario, say the more pessimistic one, it's $140 roughly a year, and you're saying that is probably comparable to what a laborer would make today, or let's say right now.
Correct. We were informed that the clients are making roughly $2 a week, which comes to about $104 in a year's time. So the third scenario is the worst scenario that I can come up with that gets it just as close as possible to $104. If I change the 3 days to 4 days, that number changes to about $67. So they actually making less.
Right. Yeah. Okay. Okay. No, I like the way you approach it, and yeah, I mean it's been a while since I've been in Uganda, but I mean think about what that number means. I mean, $2 a week. I mean, that's pretty. It's when it's really amazing to think about that. But even so, that's kind of the worst case scenario. But even if you bump it up a little bit, your optimism of the scenarios, it's a drastic increase to what they're making now. So I think that's really great. Maybe just another comment, not really a question. The other thing to think about when you're, and really in general, the main thing I was thinking about when I was doing some projects over there is, the need, right? A lot of times people do this, and the need's not this, but let's say a project, whatever it is, and the need's not there. And if the need's not there, the demand's not there. Well, what the heck is the point? But this, the demand is there. So, when you're doing a cost analysis, the demand has to be there, and it definitely is. I remember seeing, rock pile after rock pile. The reason being is not because there was no demand, but just because there was a lot, and that people would come and pick up the gravel and do their construction. So it's a high demand. So I don't think that's an issue. So once it's being made, I think it would definitely be used. So no, it looks great. I guess maybe some general comments on this. What did you guys find the most challenging? I mean, what was it? The ideation and maybe what you think would work, what not, more the technical aspects, how to get, say, the crusher to do its thing. I would like to, hear where you guys had to think.
I would say a very general problem or obstacle that the entire class came over was trying to make a mechanism that would work and be durable with such a tight budget, especially with materials that we're purchasing at retail price. We don't get this at wholesale price, so we're trying to make this thing last as long as possible and because it needs to last for a long time, it has to be able to be durable, and when this does break down, it has to be able to be built again, but at a reasonable cost at retail price. So that's one thing that was a problem. That was hard to do.
Yeah. Right. Yeah. No. Absolutely. It's a good point. And we might have talked a little bit about this before. I think the biggest thing, and I'm glad you guys put a lot of thought into it, is the durability and is the sustainability. So, I mean, things are going to wear and things are going to break, right? I mean, it's a fact of life, and it seems like you guys have put that into thought. But on the flip side, you want things to be as durable as possible. And even if, $960, I think it was $960 roughly,
yes.
the total cost?
Yes, it was.
That is a lot in terms of, say a group of Ugandans were to, say, purchase another one or totally replace it. That is a lot, but, it's not insurmountable. So as long as it's durable, I think something like 960 is definitely doable. And even with some of your scenarios, right? So this is how much an operator would make per year. What would be, good, and this is more on the personnel side, is set a little bit of that aside, say each truck bed, right? And use it for, say, replacement parts, or use it for the next rock crusher.
Okay.
Yeah. So yes, and then this goes back to the sustainability. And then I guess maybe think of another technical question. My last one with the sifting system. So the different sizes, and I don't do much construction, but given the different sizes, is there different things that it could be used for? For instance, I don't know, the smaller rocks being used for application A, and the larger gravel being used for application B. Do you have a sense of what that might be?
So not really. At the beginning of the semester, we were just told that the two sizes they want is 1/4 inch and 1/2 inch, and we were told they get more money for 1/4 inch rocks and slightly less for 1/2 inch rocks. But she didn't tell me what they use each type for. I know they use them for construction, but they never actually told us that one type is used to make walls and the other is for flooring or something like that. But
okay, right.
And so on the sifting system, we actually just went with the 1/4 inch to make them all 1/4 inch, since they get more money for that.
There is the possibility of changing out the sifter. So if you wanted to recreate the whole sifting mechanism, which is essentially a 2x4 and a wire mesh, you could change out the sizing to instead use a 1/4 inch mesh, which you could interchange with this 1/4 inch mesh.
Oh, okay. That's nice. Gives you more flexibility. Okay. Well, yeah, great. I mean, that's all I had on my end. Again, I want to thank you guys for all the hard work, and it's really nice work.
Thank you.
Thank you.